So our goal now is to count derangements, but in order to do that, we need to talk about inclusion, exclusion. So this is a basic principle in mathematics, which is really a statement about sets and counting unions. If I want to count the number of things in a triple of sets, so if A union B union C, and it doesn't matter that I have 3, I could have more. How do I do that? Well, let's take our 3 sets. So here are 3 sets, and maybe we'll give them names. This will be set A, this will be set B, and this will be set C. How do I do that? Well, I can start just by counting everything that I see that's in A, plus everything I see that's in B, plus everything that I see that's in C. And when I do that, I want to think about these regions that I've divided my space into. I'm going to think about how many times have I counted them. Well, when I counted A, I counted this region once, this region once, this region once, and this region once. And then when I counted B, I counted this region, here, here, and here once. And then when I counted C, I've got 1, 2, 3, 4 regions that I counted. And so I can see that when I'm looking on the outside, this region here and this region here, the sort of outermost regions, are correctly counted. I've counted everything in those intersections once. But in these inner regions, slightly inside of here, in this little trefoil, I've overcounted things, so I need to correct for that. Okay, so I'm going to correct for that by subtracting away. So what I'm going to do is subtract the size of A and B, and the size of A and C, and the size of B and C. And now when I do that, I can say, okay, well, if I'm going to go and subtract A and B, then I'm going to take 1 out of this and 1 out of that. And when I subtract A and C, I'll take maybe this one and this one. And when I take B and C, I'll take away this one and this one. And now what happened? Well, now this region, and this region are correctly counted. But deeper in, I've still overcounted. And what's happened? Well, I've counted everything once and I've subtracted out once. So I still need to add that back. So I want to count that once. So now I'm going to get the size of A intersect B intersect C. And we can see the general pattern. The general pattern that I'm going to have is you start at the top level and you're going to count singletons. And then at the next level, you're going to subtract doubletons. And then at the next level, you're going to subtract tripletons. And then you go with quadruples. And you're alternating. That's the inclusion, exclusion. I overcount, I oversubtract. I overcount, I oversubtract. How does this relate to the derangement problem? Well, let's remember what the derangements are. So the derangements are these sets Dn, which is going to be the set of permutations in Sn, such that Wi is not equal to I for any I. So on the surface, that doesn't look like an inclusion-exclusion problem. But the reason it doesn't is because I have this negative condition. And negative conditions are often better to work with if you flip them. So what do I mean by that? Well, I can take the complement of derangements. So that's going to be Sn minus Dn. And this is going to be the set of W and Sn such that Wi equals I for some I. And now that's exactly what's going to give me sets. And why is the problem equivalent? Well, I know how many permutations there are. This Dn is the number I want to count. So if I can count this, I'm done. Well, how can I count that? Well, if you fix I for some I, think about which I you fix. So I'm going to let AI equal the set of permutations W and Sn such that Wi equals I. And that's a specific I. And now I have to be careful because can I count that? This formula that I have up here relies on the fact that I can count intersections. And the point is that intersections are easy to count. Unions are hard because unions are inclusion, exclusion, but intersections are easy. So can I count these? Well, let's see. So how many things are there in AI? Well, first of all, does it depend on I? Not really. If I'm fixing the first letter, then I know how many things there are that I can screw around with all the rest. And it's the same if there's I. So this is going to be n minus 1 factorial. Because I fixed the letter I, but for all the rest of the j's, wj is free. So I only have one constraint, so I've narrowed that down, and now I have n minus 1 other things to do. Okay, great. What about intersections? Can I count intersections? Well, let's try it with 2. What's AI intersect AJ? And I'm assuming that I is not equal to j. Well, I fix I, and I fix j. So there are n minus 2 other things to screw around with. So I get n minus 2 factorial. And in general, if I'm going to say that I'm going to take k of these sets, then I'm going to get the intersection of AI1, AI2, up to AIK. What I get is n minus k factorial. And I'll say the hardest thing about this problem is actually coming up with notation that you can follow. But okay, this isn't so bad. So I know how to count these intersections because this condition is a very specific condition that restricts things and reduces the problem to something smaller. So now how can I use this? Well, I can think about this. How many choices are there? How many choices are there for this tuple? So how many choices for I1, I2, up to IK? So these are the numbers that I'm going to fix. So of course, when we were up here, I have n things to do, but now here I have to pick 2 things. Well, that's n choose 2. Down here, I choose k things. So the answer here is just n choose k. Choose which k things you're going to fix. So then what's our formula? So our formula for the number of permutations in Sn such that, well, let me write it this way. Our formula for the size of A1 union A2 union all the way up to AN, it's going to be the sum from k equals you have at least one thing, you have at most everything, and we're going to have choose which subsets you're going to pick. So choose k fixed points. And now you're going to take the cardinality of AI1 intersect AIK. The point is it doesn't depend on what your choice is. And we've seen what this is. So this is intersect k sets. And maybe I'll just actually go ahead and write that as n minus k factorial. K sets A1, AI1 intersect AI2 intersect AIK. The point is it doesn't depend on which sets you pick. And now we have to do the inclusion exclusion bit, which is -1 to the k minus 1. And it's k minus 1 just because when you take one thing, remember we started out with a positive. And that's it. But of course we can simplify this a little bit. We can massage this a little bit because what is n choose k? Well, it's n factorial over k factorial n minus k factorial. So let's work this out a little bit. So this is, whoa, not that much. So this is equal to the sum from k equals 1 to n of n factorial divided by k factorial minus 1 to the k minus 1. So what is that? Well, the n factorial doesn't depend on k, so we can pull that out. K equals 1 to n of minus 1 to the k minus 1 over k factorial. Great, so what is dn? Well, dn, if you'll recall, over here is n factorial, sorry, it's going to be n factorial minus this number that we just got. So it's n factorial minus n factorial times the sum from k equals 1 to n of minus 1 to the k minus 1 divided by k factorial, which of course we can just factor out that in factorial, we can distribute that minus sign in there, and we're going to get 1 minus the sum from k equals 1 to n of minus 1 to the k over k factorial. But of course, 1 is the same as minus 1 to the 0 over 0 factorial. So this is actually the same as just taking the sum here. So maybe we'll move this guy a little closer, and maybe I'll write it a little neater for you. So this is just the sum from k equals 0 to n of minus 1 to the k over k factorial, which is basically n factorial over e. And that's the formula for the derangement numbers. So basically, because this is the generating function, or the Taylor series for e to the minus 1, because we have minus 1 here. And so it's about, 1 over e is about a third. So if you just take n factorial divided by a third, that's pretty much the derangement numbers. And let's see if that meshes. Let's just really throw caution to the wind and just draw a little circle in here. Remember, our derangement numbers that we got for dn, they were equal to, well, let's do a little table, we'll have n, we'll have Sn, and we'll have Dn. So 1, 2, 3, 4, 5. Sn is, of course, n factorial, so this is 1, 2, 6, 24, 120. Dn we saw was 0, 1, 2, 9, and 44. And you can see that roughly what we're getting here is, well, this is a third of 1 is 0, truncated to the nearest integer. A third of 2 is about 1, yeah. A third of 6 is exactly 2. A third of 24 is roughly 9. And a third of 120 is roughly 44. So here we can take 1/3 of n factorial to get a rough approximation. If you want a better approximation, it is actually going to be the nearest integer to